The last talk will be given by Konstantin Delchev, and the title of his talk is Some Recent Results on Two Distance Codes.
Thank you. So, some recent results on two distant codes. This is essentially what we will see. We will give some basic facts and definitions about how we actually approach coding theory with linear programming bounds. We will see what are the conditions for attaining the linear programming bounds and give some examples for that. See what else we can do with a connection between Hamming and spherical codes. Basically a way to go in another space where we can do these bounds, and then go through some constructions and some table results in brief, probably. The non-classical stuff that I speak is based on research that we've done with Professor Boyvalenkov and Zinoviev. This has been going on for a while, and it started about 3-4 years ago with this, when we figured out that, okay, two distance codes is not something new in coding theory. It has been for a while. It's a classical topic, but two neighboring distances, Hamming distances, of course, were not something that was studied. Usually a configuration of two good distances, good in the sense that they produce large cardinality, was studied, but not always two neighboring distances, and furthermore most codes that were studied were also good, namely linear, while the non-linear case was, how to say, left for later, and we figured out that, okay, maybe later is now. The main definitions that we have, so Q is just a set of numbers from 0 to Q minus 1. It can have other nice properties if Q is nice, and if we needed to have such properties, then N and D cube code is basically a subspace of Q n with this cardinality and minimal Hamming distance between two different elements D. Hamming distance, this is the number of positions in which two elements of the code or code words exist. So basically, this has Hamming distance too. These two positions do not agree with each other, and the first one is hello. Okay. And the curves that we will back, I told you.
Тока нещо се...
Okay. So, but generally we will proceed with this type of denoting the codes. Here we will write the two distances d and d plus delta. And again, it's a set in Qn with cardinality this one, and distances which are either d or d plus delta. And the main problem of coding theory is find A, Q, and D, so they'll set the largest cardinality for which a code with these parameters exists. So here we have an issue. We want code with large cardinality and large minimal distance between two of its code words, but naturally the two do not agree, so the problem is interesting. Furthermore, in the classical case, it's actually motivated by data transmission, the so-called error correcting codes, which were and still are used when we have a noisy channel and some information is lost. We want to correct the lost information, correct the induced errors. So we introduce redundancy. And there is a neat connection between the distance and the number of errors that the code is able to correct. This is a lovely practical application which motivated the beginning of the field, but this is not why we study codes now. They are just wonderful algebraic, combinatorial, and sometimes finite geometrical objects. In our case, we will look into this by the largest cardinality for which this code exists. And one way to approach this is build nice constructions and so on. The other way is to create some kind of analytical bounds, telling us that we can't have a code that nice, and one of the classical ways to do that is the so-called linear programming method. It was started by Lemmerstein back in the 70s and goes up to Seidel. Essentially, it relies on the existence of a set of nice polynomials which have a nice addition property which connects them to the orthonormal basis of some nice spaces to which the big space is decomposed. And for Qn, these polynomials are the normalized Kirchhoff polynomials. They're orthogonal polynomials, which are equipped with a nice formula. And okay, we use this form with this substitution instead of the actual Kirchhoff polynomials. This is related to us using actually inner product and not distance. They enjoy this recurrence relation of second degree, and these are the initial conditions. Generally well-studied object that we can work with. So the two most important facts, okay, they're orthogonal with certain measure. They also have this addition formula for, again, I said, certain unorthogonal spherical harmonics. Based on that, we can easily, combinatorially, deduce the following main identity, and it's just proven by calculating the sum of all, the sum of the a given polynomial over two inner products in two different ways. One uses the identity and uses the fact that every polynomial can be expressed as a sum of our Kirchhoff polynomials, which is obvious because we have one Kirchhoff polynomial per degree. And the other just takes the inner products when two of the code words are the same, and two of the code words are different. Alternatively, we can group this part in the so-called moments and shorten the main identity. And the way we approach bounds is basically wondering what will happen if this thing is either positive or negative, but with a known sign, depending on what we want to do with it, and work with this part, which gives a direct connection between a polynomial and the cardinality of a code that we are studying. And this is something that we deal with. Alternatively, we can express all this with the so-called distance or inner product distribution. Naturally, the two of these are interchangeable. We can work either with distance or with inner product. Inner products are slightly more convenient to work with on a technical level, but when you express a given product, distances look slightly better in a line. So if we say that AD, this is the number of couples that are at the distance d, and AD plus this, d plus this delta, and the number of couples of code words at the distance d plus delta, then we can reformulate the previous identity this way. And okay, using this identity, and again, making sure that the thing that we do not really care about because it's difficult to deal with has all the proper values because of the non-negativity of the coefficients. We can eliminate it, and we have this wonderful bound, which is f of 1 over f0 for a given polynomial with these two conditions. And if the bound is attained by such a code, then this holds and this holds. Here we've written the distances not d and d plus delta, but d1 and d2, because if we have more distances, exactly the same. You just add more requirements for the zeros of the polynomials, but then the same thing holds. This is why d1 and d2 are more useful. Yeah. Okay. So, what can we improve these bounds, which is very neat? Well, one thing is that naturally, by the way we have defined AD and AD plus delta, which is the number of given couples in a graph that have some kind of distance, they need to be natural numbers. So if they aren't, then this is an issue. And we also have various combinatorial considerations if they are natural numbers. So, okay, maybe they're, but then things may not fit combinatorially or geometrically. And then potentially we also have the mechanism of direct codes where we check codes in a lower dimensionality. These are various ways to improve this bound. We will mostly make use of this. And here are some classic examples of how this bound is used. So if we use a first degree polynomial, it will give us the Plotkin bound, and it's a classical bound, almost half a century. Which is, however, still useful. It's attained for many large D. It's also interesting that it has a completely separate combinatorial proof without any of this theory. But this is a particularly useful way in our case. And here's a second degree example for the general bound. When we have d and d plus delta, these two requirements, they come from the requirements of the coefficients of the Kirchhoff expansion of the polynomial, because we have f0 plus f1 q1 plus f2 q2, and we need to guarantee the proper sign of these two. Which brings to this condition, then we can have this. And furthermore, again, if this is attained, we need to have these moments. So if everything clicks, then seasonal orthogonal rate of strength to orthogonal arrays. These are, in a sense, equivalent to, in the spherical case, spherical design. Generally nice structures. And also when working on these bounds, there are some perhaps sporadic examples that are interesting to see. The first case we have for q equals 2, so the most well-known binary case. We have and for n equals 9, d and d plus delta 4, 9, so we have a maximum distance here. N is less than 10. This is the solution that we see. However, the inner products are of course roots, but the distance distribution is also possible, so everything fits. We can't make further improvements. Q equals 3, n equals 7, d and d plus delta is 2, 7, and it's less than 21 here. And we see this is the best polynomial, and the inner products are roots, but a, d, and d plus delta, they are not natural numbers, so we can claim them n equals, n is actually at most 20. So how do we arrive to these things? In the previous two analytical cases, we kind of want polynomials which have zeros in the inner products between the codes, so they are analytically constructed, and we then see what are the requirements for them to fit. Here, how do we find this? We usually approach this from a purely computational way. We construct a linear programming problem, and we applied, in our case, the simplex method. So we find these polynomials that way, which is why we call them sporadic. They are not part of some nice structure. And we can do the trick with the whole numbers for the distance distribution. If f of 1 over f0 is itself a natural number, because then we have the bound strictly attainable, and then we can speak, okay, this is the exact value of the spectral numbers. We can try to do the trick and bring them one more. Here is another case where we can do this, which is we can do everything analytically. And okay, we have one of the distances being maximal. Now here I'm giving examples when one of the distances being the maximum possible, because this is our current research. So basically this is what we do right now. So these examples are closer to maximum. But otherwise there isn't anything special in the case apart from the binary case where you can have only one number less than maximal distance. So for q equals 10 equals 4k plus 2 d equals 2k, then we have this bound. And we can use our main identity with this polynomial, and we can immediately notice that it vanishes in the inner products. And okay, it has another root. If it has two roots and its real values, of course it will have another, which is of no concern for us. So we obtain AQ less than 8K when we do all the calculations, but when we check the distance distribution or the spectrum, then we arrive to this, and it's not that difficult to see that for no value of k, this is a whole number, so we go to 8k minus 1. Basically, this is our approach for mostly spherical. For this case, q equals from 1 to n. The other thing we can do, and which actually gives some good bounds, is if we change the space where we live and we go to spherical codes from our basic Hamming codes. Spherical codes, by the way, are also very classical topic. They have been studied since the 70s, and there are a lot of results we can use. Furthermore, there we can do much of the same tricks that we do for Hamming codes. Spherical codes, as the name suggests, this is just finite sets on the unit sphere. And again, we can speak of NMS codes, but here the inner product is generally preferred even for the way we denote the codes, which is obvious. Inner product is linear for the elements of the code, each of them, and distance has some masking square roots. The mapping that we do in order to translate our problems from Hamming codes to spherical codes is the following. It's due to Larman, Rogers, and Seidel. And it goes the following. So basically we go from Q to R to Q minus 1 by simplex, by mapping each element to one vertex of said simplex. And then the code words are translated in this way coordinate-wise, so we actually start gluing simplices. And so on, to go into a vastly higher dimension than the previously known. With this, the distances d and d plus delta go to the following distances. And here, for spherical codes, we can do much the same things that we can do for Hamming codes. However, for the linear programming, we have the relevant polynomials are the so-called Gegenbauer polynomials, and they are specific case of Jacobian polynomials with two equals parameters. In usual terminology, alpha equals beta equals n minus 3 over 2. They have these recurrence relations, and this is how they look in general. Again, they are dependent on the dimension in which we live. Again, because it's the same theory in different space, we have these orthogonal relations, and we have this addition formula where VI, G, these are the non-normalized basis vectors of the harmonic spaces, and RE is the dimension. And again, we have for them the same bound f of 1 over f0, but this time we decompose the polynomials that we work with according to Gegenbauer and Osterchuk. So based on the construction that we had and knowing that we can do a lot with spherical codes, we can have this bound, which is due to Farman-Roger-Zeidel and improved by Neumeier. Let d over d plus delta equals d over s in lowest term, and this holds true, then this is true. If s equals r plus 1, then we need also this to happen. And this bound is interesting because it is attained in numerous cases. So there's a place where it is good, but there's also places where it's very far from the real thing. So it's not very stable, but still very useful. Lastly, we can also attain many bounds for these types of resistance codes when considering purely geometrical and combinatorial means. So some simple cases can be done almost with triangle inequalities. Like this no binary codes of length 10 when both are odd, when one is odd, the other is even, and there's some issue with the triangle inequality, and with these other cases, many of these are purely undergrad level problems. Here there are also these bounds which are all also interesting, and however, going in the same direction, one bumps into much less trivial problems. And this is this conjecture that we arrived into while dealing with the general problem of two distances, or could 2, 3, and 4, possibly higher 2, and the conjecture turned out to be true. It was proven by Andrei and Borubyov with the apparatus of finite geometries. Finite geometries, as we'll see, is a rather powerful apparatus in this field too. Basically, this is a short list of our approaches for obtaining bounds in our research with Zinoviev and Zinoviev. Direct linear programming with either the analytical construction of good polynomials or computerized search for good polynomials, the connection with spherical codes, and picking up cases where we can deal directly with the distances. On the other side, Zinoviev and Zinoviev were more concerned on constructions, and it turns out that the constructions of such codes are very, very rich when it comes to looking into their sources and their relations with other mathematical objects. It seems unfeasible to speak about full classification when we have d and d plus delta. We have general form of the distances. However, classifications for d and n seem feasible, and there are a lot of classification results for d and d plus 1. There might be other particular cases where this can click. So here is some list of the objects on which such constructions are based, and the first object, this is the so-called difference matrix. Let G be an abelian group for their Q, and a square matrix is called a difference matrix if component-wise difference of any two different rows contains every element of G the same number of times. And a classical result between Semakov, Zinoviev and Zaitsev says that for any prime number P and any natural number cell on H, there exists a difference matrix D of parameters PL and PH. Second very classical object, Latin square. Latin square is the usual idea. N by N, and symbols, each symbol appears once on each row and each column. This is puzzle type. However, when we go to mutually orthogonal Latin squares, things start to become very difficult very quickly. Mutually orthogonal Latin squares, where when we place them over each other, each pair of symbols occurs only once. And here we must say that, well, there's various results for the number of mutually orthogonal Latin squares for each and the full answer of this question is open, and it seems rather difficult at the current time. Something that we'll note very briefly, additive code is a code which is also an abelian group in Qn under component-wise operation. So knowing this, let's look into the various constructions that we arrived with during our study of this topic. Most of them are well known or are various modifications, some might say mutilations of existing constructions. First is the case of balls in Qn, and the ball itself is the code with two neighboring distances, but we can also add parity checking and again create such a code. And parity checking is generally a way of obtaining constructions of the type that we enjoy. Our second approach, this is what I call the mutilation, is basically damaging an equidistant code. Equidistant code is just one distance. An equidistant code produces two codes. If we delete any row, or the code works, delete the row, or if we add one position and put whatever in it. Considering this, then we can start the general idea of damaging equidistant codes. Then we can go this way and concatenate some of our balls and obtain new codes with two distances that way. Some more theoretical construction is what we can do with Latin squares. Latin squares itself are codes with two distances, and they're both codes with two neighboring distances, and they're a code with optimal, with largest distance n. Again, we can combine two different constructions and also build this. So, going on, again from the construction of Semakov and Zinoviev, we can use difference matrices to obtain codes with these parameters, and they mostly come out trivial. So these are the types of constructions that we went in our first article with Zinoviev and Zinoviev, and from them we sort of felt interesting to see what's the general case, what's D and D plus delta, where they found certain requirements for the structure of Hamming codes. However, turned out that complete classification and exhibiting such nice types of constructions will not be possible, which leads directly to the question what happens if we fix one of the distance and we fix it someplace where it is both interesting, because maximal distances are interesting, especially in the binary case where they tell us a lot in general. And this is the classification that was reached for N. Again, some of the codes are known. The Hadamard and the difference matrix codes are the type of codes that we're interested in. Hadamard codes have been around for a while, and they have such parameters. You know that they're somewhat close in parameters to the infinite family that I showed has an optimal polynomial of degree 3. However, there we have 4n plus 2, not 4n. So they are not the same. And again, the codes that we obtained from difference matrices by Zinoviev, Semakov, and Zaitsev in 1969. Latin square codes, as we also mentioned, these are codes that have distances n-1 and n, so they fit. However, there's various issues with how many of them there are. And interestingly, here we can see that some constructions arise from finite geometry. So finite geometry, again, it's not something too exotic and unknown maybe for most of the audience. It's a finite incidence structure of points and lines, and potentially again higher dimensions, where we have basic axioms about lines intersecting into a point and points lying into a line. The simplest example of a finite plane is the funnel plane, where each of the points of this triangle is a point in the finite plane, and each line plus the circle is a line. Here we have each line having 3 points on it, each 2 points giving a rise of a line, each 3, sorry, and each 2 lines intersecting in just 1 point. The theory of finite geometries have been developed for decades, and it's a very good source of both constructions and bounds for coding theory. So it is not surprising that we see codes coming from finite geometries as one of the important families of codes in this field. These are the Bush codes, the Delsart codes, and the Denniston codes. By the way, we can reach some of these, their bounds and proof optimality with our linear programming bounds. And actually, they are reached with polynomial of degree second degree. So in many cases, these 3 families of codes are provenly optimal. They arise from arcs and ovals. Arcs, this is the usual idea of an arc, so you don't have more than a given number of points of the arc line on a line. That's the idea. And finally, after giving these families of codes and these ideas for various bounds, let's see what can we see about particular cases, what happens there. I will not go the full route and showing various amounts of tables. We will just look into two. And what we will see is lower bounds, which are existing constructions that are either some of the shells or arrive from computer-generated codes. However, the computer-generated codes generated, it's via random walks with backtracking. We start from a given seed of one or more code words. We make random jumps on the distance that we want to have, and if we see that we can't go anywhere else, then we backtrack and try again. Upper bounds are the best that we can have from linear programming, either with the numerical simplex method solutions, either with ad hoc solutions that are basically polynomials that looked like they will be good and they were in some place. Already known upper bounds from previous papers, and they are taken from the very nice database of Brouwer, and the bound to spherical codes. So here for q equals 2 and d plus 1, as stable we can see that spherical codes have their very interesting field of relevance, and we also have the other approaches on the two separate ends of the interesting interval. Naturally, these are trivial codes, so we are not very much concerned about that. Again, for q equals 3 and for dd plus 1, again we see the bounds from spherical codes being relatively present. Again, the other bounds mostly present in the end. I will stop here. Thank you for your attention. I'll try to answer them.
So, any questions, remarks?
May I use, speaking about linear programming, did you use Gurobi optimizer or what did you use?
Maple. Maple is very convenient for if you don't, if you want big parameters, it won't do. Then you will have to do a dedicated linear solver. But for reasonable parameters, Maple does pretty well and is very convenient for use. So we've used Maple because we didn't employ high performance computing.
Any other questions?
You can also use, for PC, you can also use Python or Mathematica, and they will also work wonderfully.
And please, what do you understand under infinite family of bounds? You probably...
That we have a bound for certain case for every k. For every k, we get a bound for this code.
One parameter, but
yes.
Several parameters that may take infinite value. Yes?
Not sure I understood you. Sorry.
For instance, if you have one parameter,
yes,
and this parameter may take infinite value.
Yes. For every natural number k. Yes. That was it.
Okay. Let's take the speaker again.